Hello friends, my name is JEE Mains and today I am going to do some demonstrations of torque, angular momentum and moment of inertia. So our first demonstration is the spool paradox. Now if I pull this thread, you can see that this spool is rotating and it is rotating towards the direction in which I have pulled the thread. But if I instead pull the thread in this manner, then it is rotating in the opposite direction. And then there is a special way of pulling this thread in which this spool will not rotate at all. So you can see that in this third way, the spool is not rotating in any way and it is translating. Now this is the spool and this white line is the thread around the spool. Now in the first case, this thread was pulled in this direction and therefore at this point the force is acting in this direction. So this is the force vector represented, the force which was applied by my hand when I was pulling. If I see the position vector of this point at which force is acting from the ground, from the point at which the spool touches the ground, this point is also the pivot point or the point about which this spool is rotating. We have the position vector like this, where the direction of position vector is upwards and direction of the force is in this direction. Now if I talk about the torque acting on the spool due to the force, we have that torque is equal to R cross F. Therefore, through the right hand thumb rule, I can find out the direction of torque on the spool. So if I use my right hand here, put the fingers in the direction of position vector and then rotate it towards F. So R cross F. So if I rotate it like this, my thumb is directed inside the plane of this board. So it is directed inwards like this. If it's directed inwards like this, this is the negative direction. So therefore my torque is coming out to be negative. So my torque on this spool is negative, and negative torque brings clockwise rotation. So my object is rotating clockwise, and when it rotates clockwise, it moves in the direction which it was moving in our demonstration. So in the second case, we can see that the position vector is this and the force vector is this, and here the position vector and the force vector, when represented the direction, we can see through the R cross F right hand rule that the torque's direction is pointing outwards. Therefore your torque is positive torque, and positive torque brings anti-clockwise rotation. Now this spool will rotate like this, anti-clockwise. So here the second case is happening in this way. Now my third and final case, where the spool does not rotate at all, is due to the fact that the force is acting in this direction and the force direction, if extended, you can see that passes through the pivot point. Therefore if I'll make position vector from the pivot point, it will have the same direction as force. If the angle between the R vector and force vector is 0, that is, they both are in the same direction, there will be no torque. If there is no torque, then there will be no rotation. So therefore the object will not rotate at all. It will translate, so it will move because the force is acting on it, but it will not rotate about this point because there is no torque acting on this object due to this force. So my second demonstration is about conservation of angular momentum. Here I have this object. If I make it rotate and then change the configuration, it speeds up the rotation. Again, if I see I am rotating this, it will speed up. Rotate this, it will speed up, slow down, speed up and slow down. As I change the configuration, it will change its speed, even though I am not rotating it faster in any other way. It is only rotating faster because of the change in configuration. So the situation is similar to these two diagrams here. So what is happening is, in the first case, when this object rotates around this axis of rotation represented by the dotted line, it has an angular velocity omega, and due to this configuration of masses and the position vectors, it also has a moment of inertia, which is the sum of masses into position vector squared. Okay, the sum of all these mr square values for each particle of the configuration. Here what I can see that the r of this configuration is more than the r of the other configuration, this new configuration. And this new configuration, because it spins faster, is obviously having a different angular velocity. From here I can see that moment of inertia of this configuration I dash is less than the previous configuration. Now, as there is no external torque acting on this object, the angular momentum L is constant. So as this is constant, therefore the product of moment of inertia and angular velocity will be constant in both the cases. And for these to be same, if I decrease I dash, then I need omega dash to be bigger than this omega, so that I balance up the equation. Therefore, when I change the configuration and decrease the moment of inertia, my object starts spinning faster, that is, has more angular velocity than the previous configuration, to compensate for that decrease in moment of inertia, so that the total angular momentum of the object can remain constant. My third demonstration is relating angular momentum and torque. So here I have this contraption. If I will leave it like this, you can see that it rotates about this point where it is hanging, which is the pivot point. So why this happens? This happens because the center of mass of this whole contraption is around here, and this pivot point is here. So about this pivot point, the torque is generated by gravity, which makes it rotate this way. And the position vector is in this direction, and the force acting is in this direction. So from here we can see that applying the right hand thumb rule, we will get the direction of torque to be in this direction inwards. So this will be the direction of torque. Okay, so relative to the contraption, this will be the torque's direction always. Now what I have done, that if I start rotating this disc, so the disc is rotating now, and now I leave it, rather than falling down like previously, it starts rotating. So it is rotating like this. The reason behind that is that my disc is rotating in this direction like this. Therefore, through right hand thumb rule, I can see the direction of angular momentum of this. So this is the direction of angular momentum of the disc, and as previously seen, the direction of torque is this way. So if I take both the directions, I'll see that if this yellow direction is the direction of your angular momentum and this is the direction of torque, then both are perpendicular to each other. And because torque is rate of change of momentum, therefore it wants to bring the change in momentum towards its direction. What is happening here is that this direction of angular momentum will want to go towards the torque, so it will rotate like this. So it's basically going towards the torque, but as it moves, as the contraption moves, the torque direction becomes this one, and therefore it tries to chase the torque, but it will never be able to chase it because it is always 90 degrees. So if I now show you that this is the direction of angular momentum and this was the torque. So here, if I now again start the contraption, you can see that angular momentum, yellow arrow, is trying to go towards the white arrow, and because it is rotating, the torque's direction is also changing, and in this way this object is rotating altogether. You can see that the yellow arrow is trying to go towards the white arrow, and because of this the rotation is happening. Now if you are having still a hard time wrapping your head around what is happening, a simpler other way to show this is that if you, for example, see normal circular motion, what is that? The velocity is in this direction in the normal circular motion. Therefore, momentum, linear momentum, will also be in this direction relative to the point about which the object is rotating. So, therefore, the centripetal force acting on the object in the normal circular motion and the direction of momentum are perpendicular, because of which the object rotates. Similarly, here you can also see that the direction of angular momentum and direction of the torque, so direction of the analog of momentum in rotation motion and direction of analog of force in rotation motion are also perpendicular. So they should also show a similar effect to how it has been seen in the normal circular motion. So in this way you can see how your angular momentum responds to torque.